Hello and welcome to the seventh part of my series of lectures and tutorials about scale development. So for today, I'll try to talk about exploratory factor analysis, specifically how to run exploratory factor analysis in JASP and what are some of the considerations that we need to think about now when we do so. Before I continue, I'm inviting you to please like the video so that the YouTube algorithm gods will notice my efforts and promote these lectures and tutorials. Likewise, I'm inviting you to please subscribe to the channel and join the 10% of my viewers who are subscribed. Thank you very much. So for the purpose of demonstration, the variables that we will talk about today is procrastination. So we all know what procrastination is to some extent, but some argue that what we know as procrastination is actually just one side of the story, and specifically that is passive procrastination. And some argue that there is another kind of procrastination which is kind of more productive or at least more strategic, and it's referred to as active procrastination. And these two comprise the two dimensions of procrastination. So let's define what these constructs are, what these supposed latent variables are. So when we say passive procrastination, it refers to the unintentional delay of starting or completing a task due to indecision, avoidance, or lack of motivation. This type of procrastination is often accompanied by feelings of guilt, stress, and frustration as individuals struggle with managing time and overcoming internal barriers, so forth and so on. On the other hand, when we say active procrastination, it refers to the purposeful delay of starting or completing a task where individuals intentionally postpone work to experience the pressure of a deadline to optimize productivity. So apparently there are some individuals who intentionally delay the task because they wanted to be pressured because they know that they perform better under pressure. Allegedly. This type of procrastination is characterized by goal-oriented behavior where the delay is strategic and does not compromise the quality of outcomes. Active procrastinators tend to manage their time actively and perform well under time constraints. So if these things were to be true, then apparently there are two dimensions of procrastination. One is kind of the more negative one, and then the other one is the more strategic, more adaptive one. And as what we have discussed in the previous lectures, when we have constructs like this, we then develop items that serves as representative behaviors of these supposed constructs. Items that when in a scale, if a person reads them, in a person rates their level of agreement with regard to these items, the way that they respond should be informed by the true score, the actual level of either passive or active procrastination within them as internal constructs. In the example that we will use later on, we have 9 items pertaining to passive procrastination. So that's P1 to P9. And then there are 9 items also pertaining to active procrastination. And so let's show sample items pertaining to these constructs. Now, these are just hypothetical items. For example, for passive procrastination, these are possible items. I often delay tasks because I feel overwhelmed and unsure about where to start. I put off important responsibilities even when I know it will negatively affect me. I tend to avoid starting a task that seems challenging or time-consuming. I frequently waste time on unproductive activities instead of working on important ones. No? So if I read these items and then there is a response set, true of me, not true of me, the range of those possible responses, my agreement to this, if I say, yes, this is true about me, I strongly agree, for example, then those responses should be informed by the level of actual passive procrastination within me. Supposing I'm not lying, supposing I'm not trying to manipulate my scores, then my responses should be informed or determined or influenced by the actual passive procrastination in me. And let's say, for example, the items for active procrastination, we have 4 here out of the possible 9 items. I intentionally delay tasks to give myself the pressure needed to perform better. I work more effectively when I leave tasks until closer to the deadline. I often choose to postpone tasks because I trust I can handle them quickly later. I deliberately delay starting tasks to prioritize other important activities first. So these are sample items that what we might have in the scale that we are trying to develop. And assuming that we've already done what we need to do, we have pilot tested it, we have polished the data, we have already collected data from a number of participants, and hypothetically now we have the data in our hands. So how do we run exploratory factor analysis? What is exploratory factor analysis? Again, it's a statistical analysis that allows us to determine or to identify structures within our data. So, given that this is our data, exploratory factor analysis tries to kind of summarize our data set and see if there are structures within this. If some of these items are more correlated with others, and if some items are more correlated with other items. And given our constructs, we kind of hypothesize, although again this is exploratory, but we kind of expect that the passive procrastination items would form one structure and that the active procrastination items would also form another structure, forming a two-factor structure. So that is what we are hoping for. Now, before we run the actual exploratory factor analysis, let's try to make some assumptions. I'm assuming that the data has already been cleaned, meaning to say we have already converted text responses to numbers. Sometimes when we collect data, the respondents are in text, agree, strongly disagree, and they need to be converted into numbers. Strongly agree is 5, agree is 4, neutral is 3, disagree is 2, strongly disagree is 1, so forth and so on. So that's the first assumption. Second, some items might require reverse scoring, meaning to say that if the score is 5, because the item is phrased negatively, then it needs to be reversed to 1. So I'm assuming that that has already been done. I'm also assuming that there are no missing values. And if there were missing values, you have done something about it. So if right now in your data you still have missing values, then perhaps you need to impute those missing values. There are many ways of imputing missing values. I will not discuss them in this video, but I'm assuming that you've already done that. I'm also assuming that you have removed participants who are disengaged upon checking for the variability of their response. What I mean by that is if there are participants who through and through rated the items similarly, 4, 4, 4, 4, 4, 4, 4, all 4s, or all 1s, then that lacks variability and we don't want that. Now, we call these participants disengaged participants, meaning to say these participants more likely did not read the items and simply responded without even reading the questions thoroughly. So it's possible that we can remove these disengaged participants. How do we check that? You can simply compute for the standard deviation across all of these items, and if the standard deviation says 0, that means to say that there's no variability in the responses across all of the items, then that might indicate a disengaged participant. Another assumption is that you've already removed cases or participants with anomalous pattern responses, such as zigzag responses and other forms of pattern responses. Again, indicating that they might not have actually read the questionnaire as they are answering the scale. So those are some of the assumptions I have about the particular data that we are dealing with now. So if all of these have been satisfied, then we can proceed with what we need to do with our data, which are the following. All right, let's try to check for the normality per item. Let's also compute for the mean and standard deviation for these items. So let's check on their descriptives. So we click on descriptives. We choose descriptive statistics. We select all of our items here. P1 to P9, A1 to A9, and then let's click on transpose the table, and then so we have 222 valid participants. We have no missing data, so we can remove that. We now have the mean, the standard deviation. We can also remove the minimum and maximum. So our scores range from 1 to 6. So let's uncheck that, And then to check for the normality, let's click on skewness and kurtosis. So here are our results. So we have here our mean and standard deviation values. We will use them later when we prepare the table for this. Then this is the measure of skewness. I hope you know what skewness refer to, and this is the measure of kurtosis. So looking at these, they're fairly normal. What can be flagged is if the skewness exceeds 2 and if kurtosis exceeds 8. Now, this is according to Klein. So most of these are near 0, so we don't have really problems with regard to the normality of the data. That is good. Now, what happens if there are items that are not normal? Perhaps we can consider eliminating those items. If the skewness exceeds 2 and if the kurtosis exceeds 8, then that really is kind of a big problem. So we can consider eliminating those items. Next, we check if the sample size is adequate. So we do that by going to our actual analysis. So we click on factor. We have options here. We select Exploratory Factor Analysis. Now, automatically, it will start computing stuff, but we will make some adjustments still. But let's first enter our variables. But don't mind the immediate results that it will produce because we will still make some adjustments. So let's do this step by step. Now, what we need is to determine if the sample size is enough, and that is determined by the KMO. So let's check on, where is the KMO? There is the KMO. So the overall KMO is 0.925, and what do we need? We need KMO that is greater than 0.5. So this indicates that our sample size is adequate. All right, so we have satisfied that. Next, we check if the correlations among the items is sufficient, but we don't have to actually check each correlation coefficient. We can perform the Bartlett's test of sphericity, and what we want simply is a significant result with p-value of less than 0.05. So let's go back to our options and let's click on Bartlett's test. So based on our Bartlett's test of sphericity, our p-value is actually less than 0.001. So that also satisfies this. So that means to say that the correlations among the items are sufficient for factor analysis. We remember that factor analysis is based on correlation. Next, we should identify the factoring method. So the default here is minimum residual. I don't know why, but I would prefer principal axis factoring. So let's check on principal axis factoring. Next, determine the number of factors. So how many factors should we have? We have several things to consider. First of all, there are several analytics that we can look into, from parallel analysis to Kaiser's criterion, and then the scree plot. And then finally, of course, a strong consideration also is the theory. Theory-wise, we are arguing for a two-factor model. But the analytics do not always agree. So let's check what the analytics say. The default here is based on parallel analysis, but the default is based on PC or principal components. So let's switch that to factor analysis. All right. So based on parallel analysis, specifically for factor analysis, it suggests 4 factors. Although if we try to look at the loadings, it doesn't look very well. The 4th factor, 1 is a cross-loading item, and then you're only left with 1 item for factor 1. So this doesn't seem too good. So let's try to look at the other analytics. How about eigenvalues? So if we follow the eigenvalues, or based on the eigenvalues, it suggests a 3-factor model, which looks reasonable, but let's try to check other analytics. Actually, for the most part, personally, I have a strong preference for using the scree plot, of course, coupled with the theory in determining the number of factors. So let's check on the scree plot. Let's uncheck the parallel analysis result. We just want to see the scree plot. So this is what we call as the scree plot. And what you want to look for here is what you call as the inflection point or the elbow. So the elbow basically is the point wherein there is a drastic reduction in the drop of these points. And if you try to examine this, you might consider this as kind of an inflection point. You'll notice that there's really a flattening of the points after this. But one might also argue that this is kind of a more obvious elbow or a more obvious inflection point. The angle seems to be a bit sharper, and then there seems to be a tapering off of the points. No? So if I were to read this, and I guess probably I'm also biased by the theory, I might think that this scree plot points out to 2 factors. And that would be identified by this first drop, factor 1, and then the rest seems to be kind of noise. No? So the scree plot seems to suggest that there are 2 factors. No? And that also supports what the theory suggests, 2 factors also. So how do we make that decision? So according to the parallel analysis, there are 4 factors. According to the eigenvalues, there are 3 factors. According to the scree plot, there might be 4 or 2 factors. But the theory says 2 factors. So oftentimes I lean to what the theory says, not unless the analytics really are strongly against what the theory suggests. For example, previously I theorized that a certain scale has 7 dimensions, but the analytics really are saying that there are only about 3 dimensions. So I had to go with what the analytics say. No? But in this case, at the very least, no, the scree plot seems to also be agreeing with what the theory suggests. No? So I'm gonna go with that. Besides, like what I said, among parallel analysis, eigenvalues, and scree plot, I tend to rely more on the scree plot in determining the number of factors. So because in my mind, I've decided I'm gonna go with a 2-factor model, I'm now gonna switch to manual and then identify, kind of force the issue and say that there are 2 factors. Next is choose the rotation method. So there are a number of rotations here. To be safe, just go with oblique and then pro-max rotation. Go with the default. So as we are running the analysis, check the factor loadings, restrict to 0.3, but 0.5 and above is preferred. No? So these are the factor loadings. And you can see here, it's not always this case. See here that we have kind of a clean factor loading, which is kind of boring. There's no excitement. But oftentimes, it's not always this clean. So these are the factor loadings. In most cases, what I do is to set the factor loadings initially at 0.3. And if I do, let's see what happens. I want it at 0.3 because later on, I will talk about this, consider eliminating items that do not load, items that do not have factor loadings. In this case, for now, we don't have factors that do not load based on this threshold. And also, consider eliminating factors or items that cross-load. When you say cross-load, this is an example of a cross-loading item. So an item that loads on factor 1 but also loads on factor 2. I set it at 0.3 because I wanted to see the items which are potentially cross-loading. And this also gives me a better view about the items which are more strong candidates for removal. By the way, none of these procedures are standard. Many of the things that we decide on in exploratory factor analysis depends a lot on the one who is performing the analysis. So there's really a lot of subjectivity, in running an exploratory factor analysis, and different people might have different ways of doing this. But I'm sharing my way of doing this. Now, will I remove P8? Probably not, because like what I said, 0.367 is a low factor loading anyway. The ideal is 0.5, but I just wanted to see whether there are potential cross-loading. Now, had this been, let's say for example, 0.4 something, had this value been close to the factor loading here, then that might suggest that I should remove P8. But since the factor loading for factor 2 seems to be not entirely close to the factor loading for factor 1, so for the meantime, I will leave it there. Anyway, we still have a confirmatory phase that we can do, so I'll leave it as such. Now, let's try to adjust this and make this 0.5, and let's see what happens. So if we make that as 0.5, 0.5 and above is, like what I said, ideal. You will notice that item P1 is no longer loading on factor 2. So again, you might say, perhaps we can remove this. And if you're strict with your criteria, then you can remove P1. Let's see what happens when we remove P1. There will be changes in the values here. So it will reanalyze. So there, now when you remove P1, it now is telling you that P2 and P7 are also problematic. So that's what I'm saying. Let's try to make this more lenient at 0.3. Let's see what these factor loadings are. Okay, so not very far away from 0.5, so it's still kind of acceptable. So that's the consequence of removing an item. The factor loadings of the other items also changes. Now, at this stage, I probably wouldn't remove P1. We want 0.05, but then again, the factor loading of P1 a while back isn't that far off. So I might retain P1 for the meantime. So both P8 and P1, I will try to retain. Had this been any other data set, the results wouldn't be this clean. No? And when it's not that clean, then it's an iteration of removing items that are heavily cross-loading, items that are really not loading to any of the factors, and then kind of reanalyzing until you arrive at a relatively clean factor structure. So these are the factor loadings for factor 1, and you'll notice that all of these items are pertaining to active procrastination items, and this is factor 2. All of them pertaining to passive procrastination items. Is it possible that when they cluster, some active procrastination items would cluster together with passive procrastination items? Yes, that happens all the time. And so what do you do? Then you try to look at the items. Was there kind of an error in labeling the item? Or sometimes you have to think about a proper label for this construct that accounts for the fact that it's now seemed to be a combination of items which you did not hypothesize to cluster together, which makes things very complicated in some cases. But for the sake of this example, our data is very simple, and so we can have a clean factor structure. Now, what will be useful later on when we prepare the table is to show all of these factor loadings. So we'll do that now when we prepare the table, but just note that these are our factor loadings for the two factors. And then the next part is to interpret what the factors. In this case, it's easy to interpret because our items loaded to where we expect them to be. So factor 1 can be interpreted as active procrastination, and then factor 2 can be interpreted as passive procrastination. But then again, what if these items mix together? Then that would require, I guess, a different interpretation or a different labeling. And how do you do that? You have to read all of the items again. What makes these items similar? What is the underlying latent variable that would make a person respond similarly to these items? Check for the reliability, or at least the internal consistency. So how do we do that? We go to reliability and we click on unidimensional reliability. So given that all of our active procrastination items clustered together as expected, so we want to know, do people respond to these items similarly? If that's the case, then there should be a strong internal consistency within this. Now, we know that for internal consistency, the most popular measure is Cronbach's alpha. But what you will notice is that the default here is McDonald's omega, which is the more conventional measure of reliability that is being reported in journal publications. But if you're interested in Cronbach's alpha, you can check it here, coefficient alpha, and it will produce a measure of the Cronbach's alpha. But what I suggest you present or report in your article is the McDonald's omega. What is the criterion? What is the suggested threshold? They say that good reliability measure is 0.8 and above. Slightly below that tends to be acceptable as well. But in here, we have 0.928, so a very good internal consistency measure. Let's do another one for passive procrastination. Let's click on reliability, unidimensional reliability, and let's select our passive procrastination items. Is there internal consistency in answering these items? Let's also select coefficient alpha. All right, so slightly lower, but still good, 0.840, whereas our Cronbach's alpha is 0.841. What's the difference between McDonald's omega and Cronbach's alpha? They say that Cronbach's alpha assumes that all of the items have equal weight contribution on the factor score. But that cannot be assumed. One cannot assume that, let's say, for example, P6 is as good of an indicator as P4. And they say that McDonald's omega addresses that kind of issue. And that's it. So that is how you run exploratory factor analysis in JASP. All right. And then finally, something that we need to report also is the cumulative variance. So it says here 0.324. So that means to say that our data accounts for 32.4% of the variability in the constructs that we are measuring. So that's how you run exploratory factor analysis in JASP. I hope that you learned something, and please give this video a like and subscribe to the channel. I'll see you in the next video, and I'll try to talk about how to prepare a table based on this exploratory factor analysis results.